Hi guys, this is Dr. Tim Kruse, there we go. Elementary statistics. We're going to talk about hypothesis testing. I'm going to use the critical region or the traditional method. And as the problems we're going to work, we know the population standard deviation, we know sigma. So essentially what we're going to do is we're going to talk about when do we accept what they claim is true and when do we reject what they claim is true. We're going to run a test. Our test statistic is going to land somewhere in this curve. If it lands over here, we basically call them a liar. We say, no, what you say is true is not true. But if it lands over here in the white area, well, then we have to say, well, we ran our own test, and yes, we accept that what you say is true. Now, what we're going to do is we're going to do a 5-step hypothesis test, which is actually very simple. I'm just giving you a sneak peek at it here. There's 5 steps. We'll state our hypothesis. We'll draw a picture of what the rejection area would look like. We'll run the test and we'll get an answer. We'll place that answer on the graph to see whether we accept what they said or we reject what they said. And then we state that we accept or reject what they said. And then finally we interpret, this is our conclusion, and we interpret our conclusion down here. So if you're already familiar with hypothesis testing, you can kind of skip toward the end of the video where I work 3 examples. But what's going to take most of the time today is just explaining these 5 steps, where they came from and what they mean. All right, so in a 5-step hypothesis testing method, I'm showing you a method. There's other methods. Some people use 4 steps and so on. Some people put the steps in the other order. I'm just showing you what I use. This is a 5-step hypothesis testing method. A hypothesis is simply an accepted norm, what we believe to be true or what an advertised claim is. And we're just going to test what they say and see if we agree with it or not. So the first step in this 5-step hypothesis testing method is to specify what's called your null hypothesis. Null, N-U-L-L, spelled right there. That means 0. So your null hypothesis and what we call the alternate hypothesis. Now I'm going to use a subscript 0 and a subscript 1 to differentiate these. So a null hypothesis, that's what they claim is true. And this is our challenge. Well, we're saying, no, that's not true. We're going to say it's different. All right, so first step is state your hypothesis. All right, a general definition of a hypothesis is just anything that's accepted by the general public. It's an accepted claim that we want to test. So for example, a null hypothesis might be stated like this. We would say H sub 0, that means null hypothesis. Null means 0. And then a colon. And then we state what is accepted to be true. So the population, remember mu stands for population mean or population average. The population believes that this certain quantity is 50. There will be a story that goes along with this. But the accepted average for the whole population is 50, whatever our story is. And it can be worded a bunch of different ways. They could say, an advertised claim, well, this is the definition again, an advertised claim or an accepted average. Remember, mu means average. This is the average of everybody in the world, the entire population. It's also a generally accepted average or norm. So here's some different ways it might be said. It is thought the average level is 50. Well, if you see that in your word problem, you're going to write mu is 50. It is thought that the average is 50. Or they might say the normal blank, whatever they're measuring, height, weight, toe size, whatever, should be 50. They're saying the normal level or weight or height should be 50. The normal, average, whatever, normal and average kind of mean the same thing, is thought to be 50. All right? They might actually come out and say it. They might say mu stands for or represents the average amount of, and whatever they're measuring, level of glucose in your blood or whatever they're measuring. So mu stands for what is thought to be the average amount of whatever. So they might say mu stands for the average amount of glucose in a person's blood, and it is thought to be 50 milligrams or whatever. They might say this can is labeled as weighing 50 grams. So on the outside of the can, it says 50 grams. That's an advertised claim, all right? It's thought to be true. It's an accepted average. The population out there believes that there's 50 grams in this can. So the can is labeled as 50 grams. The accepted weight is 50 grams. Or it could say the population mean is 50. Well, that's what this means here. Mu means population mean. So they could just come out and say it like that. Or they might say something like, it is known. Now, how they know, I don't know that. I guess it's just generally accepted after a bunch of studies. It is known that the average length of whatever they're measuring, maybe it's a fish in this lake, maybe in this lake it is known that the average length of a fish in this lake is 50 centimeters. So it is known that the average means mu, that the average is accepted to be 50 inches in this lake. All right, now how do we challenge that? Once we figure out what they're claiming, how do we challenge that and test it? Well, we call this the alternate hypothesis. We label it H sub 1, and there's 3 different ways we could challenge it. We could say, no. I could say, there's more than 50, all right, which is called a right-tailed test. We'll get to that when we graph here in a minute. Or I could say, no, mu is actually less than 50. That's called a left-tailed test. Or I could just say, I don't know if it's more than 50 or less than 50, so since I can't decide, I'm just going to say it's not 50. Mu is not equal to 50, and that's called a two-tailed test, which we'll look at on the graph. All right. So the alternate hypothesis, H sub 1, is our challenge to the null, to the advertised claim, to the accepted belief. We're saying, no, it's not. And we have to phrase it in one of these 3 ways. We have to take a stand and say, no, it's actually more, it's actually less, or it's just not measured right and they're marking it wrong on the can or whatever. So for example, an alternate hypothesis that says, hey, the average is actually more than 50, that'd be something like if it says 50 grams on the can, but I think they're actually overfilling the can and there's like 60 grams in the can, I'd be saying there are more than 50 grams in this package or can on average. Or maybe I think they're shorting me. If I think they're shorting me, my challenge, my alternate hypothesis will be, hey, I think on average, you guys are putting less than 50 grams in this can. All right, I'm going to go weigh a bunch of cans on my own, and I'm going to see if the contents on average are less than 50. Or I could say, I just think there's not 50 grams in this can. I'm not sure if it's heavy. I'm not sure if it's light. But I'm pretty sure that on average, these cans do not weigh 50. So maybe I'm saying, whatever's loading these cans is out of whack, and it's not hitting 50 very often. Sometimes it's light, sometimes it's heavy. But I'm saying on average, my challenge is that there's usually not 50 grams in this package. All right, so step 2. Now that we've stated our hypotheses, now we're going to graph the critical region, which I call the rejection region. All right. This is the area where if our test data lands in this area, I get to reject what they said. I get to say, you were wrong. I reject what you said. So here's my first example. Let's say that the null hypothesis, the accepted claim, the accepted average is 50 whatever. Let's just stick with there's 50 grams in this can of whatever. So the accepted claim, the advertised claim is that there's 50 grams in this can. And my challenge is, no, there's not. On average, I went out and weighed a bunch of cans, and on average, there was more than 50 grams in the can. So I'm kind of accusing them of false advertising. This is their claim. I'm challenging it. All right. Now, A, lowercase a stands for alpha, and that stands for our level of significance. Now, this will be given to you on the problem. It just depends on how accurate they want you to be. A level of significance means, is your average, we're going to go out and run our own test. We're going to grab 50 or 100 cans, and we're going to weigh them, and we're going to average that weight. That'll be X bar, so the average weight of our sample. Now, let's say it does come in a little bit more than 50, all right? Maybe I go out and grab 100 cans and I weigh them, and their average weight is 50.02 grams, all right? So yes, my average was higher than 50, but it wasn't enough to matter. If it's just 50.01, my average is 0.01 higher than what they claimed, nobody's going to care. Your test average has to be different enough to matter. That's significance. Is your data significant? So what if we measured a bunch of cans and their average weight was more than 50? So what if it's just a little bit, like 0.01? All right. But if it's a big deal, like maybe I grab 100 cans and I weigh them, and on average they weigh maybe 60 grams, well, now that's a big deal. Now that's significant. And we're going to run a test and see whether our data is significant or not. It's got to be different enough to matter. It's got to be significant, the data that we measure. All right, here's kind of what our graph is going to look like. So first of all, let's start with where is this z value? Now, I've already told you it's 1.645. What this is kind of where we draw the line, all right? Where do I decide that I can reject what they claim, or I have to accept what they claim? So where do I decide where to put this line? Well, it depends on alpha. If alpha is 5%, they gave that to us. If alpha is 5%, that's 0.0500. All right, that means there's 5% here, and there's 95% here in the white area. So 95% here, 5% there, for a total of 100%. Now we're going to use z because if you are given, whoops, it was given on the other page. If you're given the population standard deviation, if you're given sigma, we use a z-score. So I need to translate whatever my story problem is, I need to translate it into a z-score so that I know where to draw this line and I know where to shade in my rejection region. All right. So given a alpha, given a level of significance of 5%, I need to look up this z number. Well, if there's 5% here, there's 95% here. And I can look up 95% area in the z table and find out what z number produced that. So pretend you don't see the z number there. Let's grab our z table. And I want to grab my z table, and here's all my areas. And I want to find the area that produced 95%, or 0.9 or 0.9500. So I'm looking in here for 0.9500, and gosh, it looks like it's just exactly halfway in between these two numbers here. Well, let's see where that is. That's 1.6, and then halfway in between these numbers would be halfway in between 4 and 5. So it's going to be 1.645. All right, halfway in between these guys would be 0.045. 1.645. That's where that number came from. Now I have a handy little table on the bottom here that actually tells me that right here. What I'm doing, I'm looking at a right-tailed test because my challenge was that no, there's more than 50. It's greater than 50. Since it's a right-tailed test at a 5% alpha level, they've already figured out for me that I want to draw the line at 1.645. Okay? If it was a left-tailed test, I'd be on the other side of the graph. I'd be on the left side at negative 1.645. And if it's a two-tailed test, we'll get there. I would draw a line at both of the 1.96s. Over here, I have the same thing for alpha equals 1%. These are the two most common alphas, usually 5% or 1%. If it's anything else, we're going to have to kind of look it up in the table the hard way. Okay, so that basically completes step 2. Step 2 is to draw your graph, figure out where to draw the line. If alpha is 5%, I need to look up 95% on the table and find out that z is 1.645. So remember, 0's in the middle. This is 1 step to the right, and that's about 1.5 steps, a little more than 1.5 steps to the right. So 1.645 steps to the right is right about there. I'm going to shade to the right because my challenge is greater than. If it's greater than, you shade to the right. If it's less than, you shade to the left. And if it's different from, you shade both ends. Right now we're doing greater than. So that essentially completes step number 2. But let me kind of explain what it all means here. All right, if we do a calculation, I'm going to show you this in a second. If we do a calculation and we run our own test, which we're going to call z star, that's our test statistic. So if we do the math and we run a test and our test statistic, the number that we come up with, lands anywhere here in the white area. I put a dot there just to have something to point to. but it could land here, 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 anywhere in this white area, in this 95%. If our test statistic lands anywhere in that white area, we run our own test and our average, maybe I grab 100, 200 cans and I add them up and divide and get an average, and it lands anywhere in there, our average is not significantly different from what they claimed. They said on average a can weighs about 50 grams. If I land anywhere in this white area, I have to agree with them, all right? Because even though my z-star might be a little bit different from theirs, even though my test might give a mu that's a little bit different than their mu, it's not enough to matter if it lands in this 95%. So if it lands in the white area, the 95%, I must say I was wrong. All right, I challenged you. I said that cans on average weigh more than 50, and I ran my own test, and my results were not significantly different from what you said. So I have to say, never mind, I was wrong. I accept what you said. All right, officially, instead of using the easy wording, accept HO, statistics chooses to use a really difficult wording, fail to reject HO. It's kind of like admitting guilt. I tried to reject what you said and I failed. So it's kind of a hard way to say, okay, I accept what you said. All right, but on the other hand, this little sliver over here, this 5%, if we run our test, which we're going to call z-star, and my z-star lands anywhere in that shaded area over here in this 5%, well, that means I kind of win, all right? I challenged them, and I landed out here. Technically, what this means, if this is a 5% rejection region, what that means is there's only a 5% chance that I'll get this wrong. If I choose to say that they're wrong, if I choose to reject HO, there's only a 5% chance that I'll mess up. So it's kind of like in Vegas, do I take that bet? Yeah, if there's only a 5% chance that I'll lose, I'm going to take that bet. It means there's a 95% chance I'm right if I reject HO. So if, however, my test dot z-star lands here, we win. Our average is significantly higher than what they claimed. They claimed that on average the cans weigh 50. I weighed a bunch of cans. I calculated my statistic. I had a lot higher average, significantly higher. So the average of my cans was a lot higher than what they claimed. So I win and I get to say, no, you're wrong. I don't accept what you said. Officially, we say I reject your null hypothesis. Okay, so here's what the other two situations would look like. Let's say that I challenge and say, no, on average, there's less than 50 grams in each can. So since it's less than, remember less than is to the left, all right? So less than shades this area over here. Now I changed my percentage. I changed my alpha to 1% just to show you that alpha changes. Sometimes it's 5%, sometimes it's 1%, sometimes it's something else. So what if my challenge was, on average, your cans weigh less than 50 grams, and I want a significance level of 1%. Okay, that means there's 1% here and 99% here. 1% is 0.0100, 99% is 0.9900, all right? I got to figure out what this z number is that has this area. In the z table, it measures area to the left. So I'm looking for a z number that produced 1%. I'm looking for a z number that has an area of 0.0100. So let's do it the long way first. Let's grab my z table. Now I'm over on the negative side. Remember that. Here's 0, -1, -2, -3. So I'm in the negative z's. So when you grab your z table, grab your negative z. And I'm looking for 1%, 0.0100, or as close as I can get to it. All right. Now look right here, 0.01. That's 1% and a little more. That's 1% and a little more. That's 1% and a little more. Ooh, that's close. All right. This is about as close as I can get. This is about 2 away from 1%. This is only 1 away from 1%. So that's the one I'm going to choose. I'm going to choose negative 2.33. So remember, the z number tells you where to draw the line. Where do I draw the line about when I reject and when I don't reject? Well, the z number says, okay, if you want 1% to the left, shaded, you need to start at z equals negative 2.33. So here's 0. There's 1 step to the left, 2 steps to the left, and about 1/3 of a step to the left further. So it's about 2 1/3 steps to the left is where I draw the line and shade to the left. Now, after this, I would run a test and see where my dot lands. If my dot lands anywhere here in the white, I kind of lose. I have to accept what they said. But if my test statistic lands anywhere here in the shaded area, even though it's really, really small, if my test statistic lands over here, I get to say, haha, I reject what you said. I reject your claim. I don't think your claim is accurate. You said there's 50 in each can. I say there's less. I'm right. I reject what you said. And then finally, if we just don't know if it's less than or more than, we're just going to say, I just know that it's not 50. You know, it could go either way. And once again, I changed alpha just to show you a different look at alpha. My level of significance now is 10%. Well, if I don't know if it's less than or greater than, what I have to do is kind of split the difference. I got to say, well, there's some that will be too light and there's some that will be too heavy. This is called a two-tailed test. Left tail, right tail. When you use both of them, it's called a two-tailed test. So when I weigh the cans, some of them could land over here too light and some of them could land over here too heavy. Now again, where do I draw the line? All right, pretend you don't see the Z number here. Where do I draw the line? Well, you have to think about the alpha level. If I have an alpha level of 10%, okay, example 3 magically changed. I had to pause the video because I had that one messed up. So, you know, good lesson in mathematics. If you mess up, just grab your eraser and fix it. So my alpha level is 10%, all right? And the question is, where do I draw the line for my left tail and my right tail? I got to look up these Z numbers. Now, it'd be nice if there was a 10% in my handy dandy little alpha table here. So I'm looking at alpha equals 5%, alpha equals 1%, dadgummit. I'm looking for the critical values. That's where I draw the line for a two-tailed test. We're working on a two-tailed test. And all they're giving me is 5% alpha. You would start at both the 196s. And if you want 1% on each end, you'd start at both the 258s. But they don't have alpha equals 10% here. So we got to kind of do it the hard way. And the hard way is just kind of figure out what's in each section. So if alpha is 10%, now 10% is my rejection area. That means this area and this area together need to add up to 10%. Well, if I want to split them in half, that means 5% on the right and 5% on the left. So if you have a two-tailed test, and you want to take your rejection area and divide it into two parts. So if it's 10% total rejection area, I want to split it into two parts. That means 5% here and 5% here. So that's my question. All right, I want the Z number that gives me an area of 5%. I'm not going to look up this one here. It's kind of too difficult because it tells me area to the left, and I have a couple of areas in here. So let's not try to look up this one. Let's look up this one here. I can look up area to the left. So I'm looking for a negative Z number because I'm left of 0. So I'm in the negative Z's here. I'm looking for a negative Z number that gives me an area of 5%, 0.0500. So let's kind of do it the long way here. Since our little table didn't help us out, let's get on the right table. All right. So I'm looking in my negative Z numbers, and I'm looking for 0.0500. So I'm looking for 5%. And I just kind of scroll around in here, and I look and I look and I look. Oh, there's 5% and 26 extra. There's 5% and 37 extra. I'm getting pretty close. Here we go. There's 5% and 5 extra. There's 5% and 5 less. So this one here, it's exactly halfway between. That's negative 1.6. And then we go up here. It could be 164. It could be 165. It's actually halfway in between. That's negative 1.645. All right. So I found this Z number right here. I went to my table and I said, okay, which Z number gives me an area of 5%? And I looked up this in the table. It was Z equals negative 1.645. Since this white area is exactly in the center, that means the other tail is the same number, just positive. All right, so that gives me 5% to the left, 5% to the right, with 90% in the middle. All right, kind of a long way to do it. It's nice if the alpha level is in your little cheat table at the bottom, but if it's not that hard to figure out. Just figure out what this area on the left is, look up the z number that produced that area. Once you find the negative number, the positive number will be in the same place. So one step to the left, and then a little more than half. Negative 1.5 would be 1.5 steps to the left. We want to go a little bit further, about there. Same thing to the right. All right, so now that we've got a picture, let's do a little bit of math and just see how our test wound up. Maybe I grabbed 50 cans and weighed them. Maybe I grabbed 100, 200. Maybe I grabbed 1,000. It's however many cans I grabbed. I weighed them all, I add them up and divided by how many there were. And now I'm going to convert that X data, whatever that average weight is, I'm going to convert that to a Z number. So I'm going to convert whatever my X data is. Maybe I weighed 100 cans and the average weight was 54.35. Well, I need to convert that 54.35 to a Z number, to a 0, 1, 2, 3 number, so I can put it on the graph and see where it landed. All right. So this formula right here is just a conversion formula. It's going to convert our average weight to a 0, 1, 2, 3 Z number. Then I can put a dot on there, see where it landed, and make a decision. All right, we're just going to call this Z star. Now, why are we using Z? Because in the problem, they'll tell us, they'll say this is a normal mound-shaped distribution. They'll say something like that. And also, they'll tell us what sigma is, what the population standard deviation is. Once they tell us both of those, I know that I can use Z. Now, if they don't tell us sigma, we have to use the t value, all right? But we're going to use a z-score because we know sigma. Using the t value is another lesson. So to calculate my test statistic, z star, I find out how far my average differs from their advertised claim, and then I divide it by standard deviation. Now we have to adjust the standard deviation for the small sample size, but this tells me how many steps left or right I need to go. All right, so back to example 1. For example, all right, for example, example 1, I said I'm going to shade this much to the right. I'm going to shade 5% to the right. That means start at 1.645 steps to the right, draw a line, shade to the right. If it lands here, if I do the calculation, and let's say, for example, I get a 2.15. I did all my average weights. I weighed all those cans. I added them up. I divided by how many there were. I got an average weight, and I converted it to a Z number. And that Z number is 2.15 steps to the right. Okay, that's 1 step to the right, 2 steps to the right, and a little more. It landed right there. All right. This is the rejection area. This is where I win. I get to say, look, I weighed a whole bunch of cans. My average weight came up much heavier than your average weight, significantly heavier than your average weight. So I reject your claim. I reject that you say the average weight of this can is 50 grams because I weighed a whole bunch of cans. I changed that weight to a Z number. I placed it on the graph, and my results are significant. If, however, I do the same thing and my average weight is a little bit lower and I convert it to a Z number and maybe place it here, it could be anywhere here in the white area, but maybe I place it here, well, then I have to say, I challenged you and my results were a little bit lower. See, this is 0. This is kind of mu. My results were a little bit lower, a little bit off of yours, but they weren't significant enough to report. So I just have to say, okay, I accept what you said. So the easy way to say it is, I accept your claim, but we have to say it the hard way in statistics and say instead, I failed to reject your claim. You said mu is 50. I tried to reject that claim, and I failed. You have to kind of admit guilt. All right, and then step 4, once you figure that out, you just state your conclusion. You're either going to say I reject HO or I fail to reject HO. That's nice and easy. All right. The only problem is nobody understands what you're talking about. Nobody who's not a statistics student. Okay, so anybody who's not a statistics student doesn't know what you're saying here. So we have to move on to step 5, which is interpret your conclusion. We have to explain what we came up with to the average person on the street. And the interpretation seems a little confusing at first, but there's really only a difference of one word between your interpretations. So the last step is interpret your conclusion. All right, I'm back to example 1. I'm still using example 1. So if you fail to reject HO, that means you weighed a bunch of cans, you got an average that was a little bit off of what they said, but it wasn't enough to make any difference. So you tried to reject what they said and you failed, all right? Well, then you say something like this. You say, I didn't have enough evidence. There is not enough evidence. You tried. You weighed a whole bunch of cans. You came up with an average that was a little bit different from theirs, but it wasn't enough, all right? So I didn't have enough evidence at the whatever level of significance they tell you to conclude that, and then basically you just restate what your challenge was, all right? Same thing for reject. Let's say you win and your test statistic landed in the shaded area and you get to reject what they said. You say something like the exact same thing, except you say, I did have enough evidence. So notice there's only one word difference between your two interpretations. You either didn't have enough evidence to back up your challenge, or you did have enough evidence to back up your challenge. All right, so let's work through real quick. Gentle Ben's a Morgan horse at a Colorado dude ranch over the past 8 weeks. A vet took the following glucose readings from this horse. So took 8 separate readings, probably a week apart, and measured the glucose readings in this horse. You know, maybe this horse has been feeling badly and they're going to check its blood sugar, its glucose. So the sample mean, let's add these all up and divide by 8. So the veterinarian's sample average is 93.9, all right? Now, is that a big deal? Well, we got to run a test and see if it's a big deal, all right? Let X be a random variable representing glucose readings taken for Gentle Ben. We may assume that X has a normal distribution. That's something they have to tell us. So we can assume that our distribution will be normal and mound-shaped like this. And we know from past experience, that just means maybe a bunch of vets have measured a bunch of horses and they've come up with a standard deviation, a population standard deviation of 12.5, all right? So they're given that. The mean glucose level, this is for every horse everywhere in the world. The average glucose level for any horse should be, and then they're telling you this is for any horse in the world, should be 85, all right? Do these data indicate that Gentle Ben has an overall average glucose level higher than it should be? They're saying it should be 85. And they're saying, is his significantly higher than 85? We came up with a test. We tested him 8 different times over a span of 8 weeks. And we came up with an average glucose level of 93.9. Now, yeah, that's obviously higher than what it should be. The population average is 85. Any horse in the world should have a glucose level of 85. Gentle Ben's glucose level is 93.9. Now that's higher, but is it significantly higher? Is it so high that we need to give this horse medication? That's what we're trying to figure out. And they said use an alpha level, a level of significance of 5%. So here I just organized my data. How many tests did I do? 8. All right. What's the population average supposed to be? It's thought to be 85. All veterinarians all over the world will agree that a horse on average has a level of 85. Give or take 12.5. So they told us the population standard deviation, sigma. If they tell us this, we can use a z-table. We can get a z-score. If they don't tell us this, we use a t-table, and we use a t-value. That's a different lesson, all right? We're going to use the z for this lesson. My sample average, those readings that I took and averaged, was 93.9. Now look, see, that's obviously more than what it's supposed to be, but is it significantly more? Sample standard deviation is unknown, but we don't need it for this calculation because we have the population standard deviation. What's your alpha level? 5%. All right, so first step, state your hypothesis. Well, they say that a horse should have a level of 85. That's the null hypothesis, the advertised claim, the accepted average. My challenge is, I think Gentle Ben's average is significantly higher than 85. That's my challenge, and they said so right here. Has an overall glucose level higher than, so they're telling you what your challenge is, all right? Notice that the null always has equals. It's basically, you're replicating this information right here. The null hypothesis is going to be a statement. The average is something. It's always going to be equals. This one here, the challenge, the alternate hypothesis, that's going to be less than, greater than, or different from. And you have to use your clue words here. This one says higher than. So my challenge is higher than, greater than. That's going to be a right-tailed test. All right, step 2 is figure out where to draw the line. All right, I want a 5% significance level. That means I need to shade 5%. Greater than means to the right. So I want to shade this tail to the right, and I want it to cover 5% of the curve. I got to look up that z number. Pretend you don't see the z number there. So I want a right-tailed test that has 5% on the right and 95% on the left. Now you can do it the long way, or you can use the little table that cheats. All right, I want a left-tailed test at 5%. Whoops, I messed up again. I want a right-tailed test at 5% level of significance. That means draw the line at 1.645 and shade to the right. So I want to draw the line at 1.645 steps to the right. Here's 0, here's 1, there's 1.5, and it's a little bit more. So I draw the line and I shade to the right. This is my rejection region. If my test statistic lands out here, I get to reject their claim. All right? Okay, now pretend you don't see the calculation here. Here's where we do the calculation, step 3, z star. This is my test. I'm going to convert my average. I said my average is 93.9. I'm going to convert that to a 1, 2, 3 number so I can put it on the z scale here. So z star is my average minus the accepted belief over the standard deviation, which is adjusted. So my average, 93.9, minus what they say it should be, 85, divided by standard deviation, which is adjusted, should tell me how many steps I need to take for my test value. So I need to take 2.01 steps to the right. So here's 0, 1 step to the right, 2 steps to the right, and just a smidge more. It's right about there. So my z star, my test, my average, when I convert it to a 0, 1, 2, 3 number, is right there, which is in the shaded region. That means, hey, I was right. All right, I reject that the average is 85. My horse is significantly higher than 85. Gentle Ben is significantly higher than 85. All right, step 4 is just simply state we reject. It landed in the shaded area. Z star landed in the shaded area, so we reject what they said. And now I have to interpret that. So what do I do with that information? There's enough evidence at the 5% level of significance to conclude that. And then here you just restate your challenge. Gentle Ben has a glucose level that is way too high, is what we're going to do with this information. So we tested Gentle Ben 8 times. We have proof at the 5% level of significance that his glucose level is significantly above average, which is bad. All right, Gentle Ben's going to need some medication. All right, you guys that are business majors, maybe you understand this question, but I don't. I just understand the statistics part of it. So the price to earnings ratio, P/E, no idea what that is an important tool in financial work. A random sample, there's sample, of 14, that's N, of 14 large banks gave the following price index ratios. So here's our 14 banks. I added them all up, I divided by 14, and I got a sample average. Sample mean means sample average. We call it X bar. It's 17.1. So this is our sample. All right, we're going to challenge the null hypothesis in a minute with our sample. So generally speaking, a low ratio indicates a value stock or a bargain stock. Suppose a recent copy of a magazine indicated that the price earnings ratio of a certain stock index is mu equals 18. Well, there they just came out and told you that the population average is 18. It's nice when they give it to you like that. Lots of times you have to read the words carefully and figure it out. Let X be a random variable representing the price earnings ratio of all large U.S. bank stocks. We assume that X is normal. They have to tell you that. And if they give you sigma, you get to use the Z table. Do these data indicate that the price, I never can remember what that is, price earnings ratio of all U.S. bank stocks is less than 18? There's our challenge right there, less than. So keep an eye out for your challenge and then use alpha of 10%. All right, let's organize. N equals 14. So we sampled 14 banks and averaged them. The average is supposed to be 18. That's what they told us right here. The average is supposed to be 18. That's the advertised claim. That's what the accepted average. Everybody thinks that the average is 18. Give or take 4.2. This is population standard deviation, which was given, which means we can use the Z table. We did our own study of 14 banks and we averaged them and we got 17.1. Now it looks like obviously that is lower than the accepted average, but is it significantly lower? We got to run a test and see if anybody cares. If it's just a little bit lower, nobody cares. If it's a lot lower, then people care. All right, sample standard deviation is unknown, but we don't need it for this calculation because we know the population standard deviation. And this time they want the level of significance to be 10%. So first state your hypothesis. And they gave us the null. Look for the equal sign. There it is again. Mu is 18. The accepted value is 18. The accepted average is 18. The advertised claim is 18. So mu is 18. That's always going to be equals. Then the alternate will be less than or greater than or different from. So my alternate hypothesis, my challenge is that, and they told us right here, less than 18. My challenge is I did my own test, and I think the average is actually less than 18. I did my own test, and I got my own results, but is it significant? Are my results are my results significantly lower than 18? Are my results significantly lower than what is thought to be? All right, let's draw a picture now. It said alpha level of 10%. I want to shade to the left. Less than means a left-tailed test. So you're trying to figure out where to draw the line to do this shading. All right, pretend you don't see the negative 1.28. Well, this is pretty easy here. 10% is not in our cheat sheet, our shortcut table. All I got to do, though, is I just got to look up an area of 10% and find out what Z number produced that area. So I'm looking for 0.1000 in the table. I'm going to look for that area, and then I'm going to figure out what Z number produced that. Remember, you're on the left side of 0. See, here's 0, -1, -2. You're over here on the negative side. So go to your negative Z table. All right, and you're looking for 10%. That's 0.0100. Here's 10% and 36 extra. There's, whoops, no, that's 1%. I messed up. So we're looking for 10%, 0.10. Gonna have to go down a little bit. All right, there's 11% and a little extra. Here's 9%, a little extra. You just keep bumbling around until you find 10%. All right, and I'm over here and I see 10% and 20 extra. All right, and there's 10% and 3 extra. Oh, I'm getting pretty close there. And this is 10%, but it's 15 short of 10%. This is only 3 over. This one's closer. That's as close as I'm going to get to 10%. So that's -1.2, and then take it on up to 8. -1.28. All right, so now we know where to draw the line. What Z number produced an area of 10% to the left? That's the Z number -1.28. So I want to take 1¼ steps to the left. So here's 0. There's 1 step to the left. That's another quarter of a step to the left. All right, again, pretend you don't see the test statistic. That's the third step, is run your test. I want to take my information, my average 17.1. I want to compare it to the accepted average 18, and I want to calculate a Z number. I want to calculate a 0, 1, 2, 3 number that I can place on this scale. So I do my calculation. There's my average minus the accepted average. And then if I divide it by the standard deviation, I know how many steps to take to the left or right. So when I do this calculation, it tells me to take 0.8 steps to the left. So here's 0. So it's not even 1 whole step to the left. It's right about there, about 0.8 of a step to the left. So my test statistic, Z star, with my information, it landed right here. Well, dang it, this is where I wanted it to land. Over here, I just have to agree with them. I have to say, okay, I tested your data with my own data. I did my own measurements. I did my own average. I changed it to a Z number. I placed it on here, and you know what? It's different, but it's not different enough to matter. All right, it is, my data is lower. Look at it right here. my 17.1 average is lower than your 18 average, but it's not enough that anybody cares. It's a little bit lower, nobody cares. It's not enough to matter. If it had been really, really, really low and landed over here, well, then that would be significant. And then I could say something. And then I could say you're wrong. But since I landed over here, I have to agree with you. So step 4 is I agree with your null hypothesis. But we have to say it the hard way. Fail to reject the null hypothesis. You claim the average was 18. I tried to reject that, and I failed. Now, kind of just explain it to grandma, what you're talking about. I failed, so I didn't have enough evidence. There's not enough evidence at the 10% level of significance to conclude that, and then just restate your challenge from the word problem. The price-earnings ratio of all large U.S. bank stocks is significantly less than 18. I didn't have enough evidence to prove that. Okay, last one. Nationally, about 11% of the U.S. wheat crop is destroyed each year by hail. If you're an insurance agent, you would care about that. An insurance company is studying wheat hail damage claims in a county in Colorado. A random sample of 16, that's going to be your N, 16 claims in the county reported the percent of wheat lost to hail as this. So 14%, 10%, 10%, etc. Add these up and divide by 14, we got an average of 12. All right, this is our measurement. This is what we're going to challenge the accepted average with. Let X be a random variable that represents the percentage of wheat crop in that county lost to hail. Assume that X has a normal distribution. They have to tell us that. And then if they give us sigma, we get to use Z. Do these data indicate that the percentage, here comes your challenge, do these data indicate that the percentage of wheat crop lost to hail in that county is different, and that's going to be not equal to, is different either way. That means it could be lower, could be higher. From the national average, okay, national average, that's a population average, that's mu, that's population mean of 11%. So mu is 11. Okay. All right. Alpha level, 1% level of significance. How many did we measure? 16 claims. All right. The national average is 11. So mu, that's the national average. Population mean, population average is 11. My average was 12. It appears to be higher, but let's see if it's significantly higher. They told us the population, give or take, was 5. Population standard deviation was 5. Sample standard deviation, I don't know, but I don't need it since I have the population standard deviation. And my level of significance is 1%. So the average, the population average, is assumed to be 11. All right, it's accepted that the population average is 11. I'm going to challenge that and say, no, it's not. Could be lower, could be higher. I'm just saying, no, it's not. The average is not 11. So this is going to be a two-tailed test. It could be lower, it could be higher. It's just not 11 is what I'm saying. All right, where do I draw the line? This one's a little harder. All right, if it's a 1% level of significance, that means the shaded area needs to add up to 1%. All right, so I have 99% in the middle and 1% on the ends, but I got to split it into two parts. So the math might be a little tricky for you. It's basically just take this and divide it by 2. All right. So if you do 0.01 divided by 2, you'll get 0.0050. What you're talking about is 0.5% here, 0.5% here, and 99% in the middle. 0.5% looks like this. It's 0.01, that's 1%. This is 1%. And then if you take half of it, you get 0.005. And then I just put another 0 on there so it'll look better on the table. Might be easier to match up something on the table. So if you take alpha divided by 2, you get 0.5% here and 0.5% here. Now I got to figure out what those z numbers are. I'm not going to look up this z number because it's too much math. I'm just going to look up this z number here. I'm going to find out this area. I'm going to go find the area of 0.0050, and I'm going to figure out what z number produced that area. Okay. So let's do it the hard way first. I want 0.0050. All right, 0.0050, 0.0050. Man, it's just pretty close. It's right in there between 51 and 49. There's 0.005 and 1 extra. That's 0.005 and 1 less. And I think they decided to go with the 8 because it's closer. I'll show you the shortcut in a second. So we're going to do negative 2.5, and we're going to stick with this one because it's closer, 8. Now that value actually is in my shortcut table here. I have an alpha level of 1%. I'm doing a two-tailed test, and they're telling me to draw the line at both of the 2.58s, the positive and the negative. All right, so 2.5 steps to the right, draw the line, shade to the right. 2.5 steps to the left, draw the line, shade to the left. That's 0.5% here, 0.5% there. Now let's find out where I land. I'm going to run my test. Here's my average. Here's the accepted average. And if I divide it by the standard deviation, whoops, that's supposed to be sigma. Let me just change that real quick. Oh, that's really ugly. There we go. That's not bad. All right, my average minus the accepted average divided by the standard deviation, which we adjust, gives me how many steps to the right or left to go. So I'm changing my X data to Z data. I'm changing it to a 0, 1, 2, 3 number. So it says, hey, your average needs to be 0.8 steps to the right. Here's 0, so it's not even a whole step to the right. It's about 0.8 of a step to the right. Dang it, I landed here, all right? So even though my average was a little bit higher than the accepted average or the advertised claim, even though it was higher, it wasn't high enough. Nobody cares that my average was a little bit higher. All I can say is, yeah, this county in Colorado has a little bit more hail damage than average, but it's not enough to be unusual. It's not significant. So I have to say, okay, I ran my own test. I measured all those counties in Colorado. Yeah, they're a little bit above average, but it's not enough that anybody cares. It's still normal, all right? So I have to say, okay, I have to agree with your accepted claim. I have to agree with HO, all right? I would rather say I agree with your null hypothesis, but we have to say it the hard way. I failed to reject your null hypothesis. You said the average was 11. I ran a test. I tried to reject what you said, and I failed. I have to accept what you said. And then finally explain it to Grandma. There's not enough evidence. I failed. I didn't have enough evidence at the 1% level of significance to conclude that, and then just restate your challenge from the word problem to conclude that the percentage of wheat crop lost in this Colorado county differs significantly from the national average. Yeah, they lost a little more than normal, but it's still normal. It's not significantly different. All right, guys, that's it.